Okay, we've been finding derivatives, and in the definition of the derivative, we do note that there are situations where this limit may not exist, right? And so we talked about the derivative maybe not existing, but we haven't seen an example of that yet. But in general, the functions we've been looking at have been sort of nice in some way. So they all have had derivatives that exist. The only exception to that was when we looked at y equals square root of x. That's not a very good picture. We saw that at 0, the derivative didn't exist because so remember that the derivative was 1 over 2 square root of x. So when x was 0, we got an undefined result. And so the domain was only values that were greater than 0. So we've seen, I guess, a little bit, but we want to talk a little bit more about how can a derivative not exist. Okay, so to do that, let's look at an example of a nice simple function, something from the first unit, our parent function being the absolute value. And of course, if we subtract 2 inside the function, we know that that's going to horizontally shift it to the right 2 units. So it's going to look something like that, assuming that's at 2. Okay, so sketch the graph of f. I don't know why I did it up here. There it is. So we can write this this function as a piecewise defined function because we can think of this as 2 pieces. One piece is the piece that's coming down, and then the other piece where it's coming up. So this function can be thought of alternatively as, so this line right here is the line, it would have slope negative x, but a y-intercept but positive 2, for x values less than 2, right? So note that's the same thing as the negative of x minus 2, right? What's happening is the absolute value is forced to be positive. So we sort of take what would have been this function going on infinitely this way, and we reflect it up over, we reflect across the x-axis to make it positive. So we make the negative of it. Okay, so all of that, what I just said, is coming from information from Unit 1. So we have this piece has slope negative 1, y-intercept of 2. So we're on this piece for values of x less than 2. But then we actually have just the original function x minus 2 if we look at values for x greater than 2. And what's happening at 2 is, well, both of these are defined to be 0. So you can assign the equality to either piece, whichever piece you want. So here or here, but not both because otherwise it's not a function. Okay, so if we find the slope now of the tangent lines through a point 1.99 is certainly less than 2, we're going to be looking at using this top piece. So the derivative at 1.99 is going to be looking at this top piece. That's the slope of this line. That's negative 1. But if we look at a piece at anything greater than 2, right? So now we're using this second piece of the piecewise defined function. Now the derivative at 2.01 is going to be the slope of this line, which is positive 1. Okay, so what's happening visually, and this is obvious visually, right? So if you look at the graph, as we're coming from the left, sort of the slope from the left, maybe I'll write that, slope from the left is negative 1, and if we look at the slope from the right, it's equal to positive 1, right? So this is very obvious visually. We've got a constant slope of negative 1 coming from the left. We've got a slope from the right going to be positive 1. So what do we think the derivative from the left of the function of f of x is at 2? So that's negative 1, and the derivative from the right is positive 1. Right? So we have this notion of limits from the left, limits from the right. The derivative is defined based on limits. So this should not be a shocking definition here, that we can think about right-handed limits and left-handed limits in terms of derivatives. So this would be the slope from the right side. This is the slope from the left side. And by the way, your textbook uses an alternate definition of the derivative here, but both work. And the bottom line is, so the regular old two-sided limit derivative will only exist if both one-sided, this should feel very familiar, both one-sided limits exist and are equal, right? This is the exact same statement we said in the limits unit, right? The two-sided limit, the derivative, the actual definition of the derivative is a two-sided limit. That's only going to exist if both one-sided limits exist, I should say that first, they exist and are equal. Okay, so this is the usual, this is what I say down here in this paragraph, the usual relationship between one-side and two-side limits holds for derivatives. In other words, the two-sided derivative exists only if and only if both one-sided derivatives exist. Look at that. I could have saved myself some writing and just underlined this right here. Okay, a function is differentiable on a closed interval if it is differentiable for all values in the open interval and if the one-sided derivatives exist at the endpoints. Okay, so we're talking about that because sometimes, like for example, if you're looking at that, go back to that function, the square root of x, the domain of this function is already only for values between 0 and infinity. And so in order to say that this derivative would exist at 0, which it doesn't, but if it did, we would have to just talk about the right hand derivative at 0. Now, this is still approaching infinity, so it's not defined at 0 in this particular example. But there are other functions that are only defined on some interval for the domain, and in those cases, we really think about the one-sided derivatives. Okay, let's look at an example. So let's use the definition of one-sided derivatives to show this derivative is not differentiable, right? So let's go to what I basically want to show is that the limit from the right, okay, so the limit from the right is equal to this. And remember that I'm using the function f of x as x plus 2 for values of x greater than 2. So I'm looking at it from the right. I'm using this piece of the definition. And of course, sorry, there's a mistake there. That's why I was struggling for a second. It's not x plus 2. Okay, it should be x minus 2, right? If we go back, let me just show you where I'm getting this from. So I just made a mistake. I want to make sure I correct it. Right, we're looking at the values for which x is greater than 2. So it's going to be the function is x minus 2. Whoop, too far. Okay, so this is going to be minus. So if we simplify this expression, the 2's cancel, and we're just left with delta x over delta x. So we just get 1. Now if we do the same definition from the left, okay, so for f of x, for x values less than 2, we're using the function negative x plus 2. So we get negative 2 plus delta x plus 2. Again, when we distribute these negatives, the 2's are going to cancel, and we're just left with negative delta x over delta x. So we get negative 1. So these two one-sided derivatives are not equal, and therefore the function is not differentiable at 2. Let's use the definition of one-sided derivatives for this piecewise defined function. Okay, so let's look at the limit from the right. If I'm working from the right, I'm using this second piece, right? Because I'm for values of values of x bigger than 1. So I'm using this piece and I'm replacing x with 1 plus delta x minus just replacing 1, right? So this is f of 1 plus delta x minus f of 1. Okay, what does this equal? Well, if we simplify what's in the parentheses here by combining like terms, this is really just negative 1 plus delta x quantity squared minus negative 1 squared. So we can expand negative 1 plus delta x times itself by distributing. Okay, so we're left with this. Notice that the 1 and the negative 1 cancel, and we can factor out a delta x from each of the remaining terms. So we have delta x times negative 2 plus delta x, and this is all over delta x. Because we have this limit written here, we can cancel because we're not looking at when delta x is equal to 0, but just as we approach 0. So we're left with just negative 2 plus delta x, and now as delta x goes to 0, we get negative 2. So the derivative from the right, so f prime of x, when we're looking at the piece for values of x bigger than 1, we see that the slope is negative 2. Sorry, as soon as I finished writing that, I realized I didn't want to say that in general because we didn't say for all values in terms of x. This was just at 1. Okay, so all we can say is the derivative from the right is equal to negative 2. Now I've used up a lot of space, but we have to repeat the same process from the left. So from the left, we're using this top piece, right? So our function is just x squared. So from the left, we have just 1 plus delta x quantity squared minus 1 squared over delta x. And if we expand, we get this. And again, the 1's cancel. And we can factor out a delta x. And when we factor out a delta x, we're now just left with the limit as delta x goes to 0 from the left of 2 plus delta x. Again, direct substitution here of letting this equal 0, we get 2. So we have the derivative from the left of 1 is equal to positive 2. So these two things are not equal, and I apologize for the not so organized work, but they're not equal, and so that's showing us that the function is not differentiable at 1. By the way, the other way to look at this is to actually graph it. Okay, and if we do that, we can look at these two pieces, and as we approach 1 here, we see that the slope coming in from the purple portion of the segment is something positive, and then it sharply changes to a slope that's negative. So certainly the derivative from the left, the slope from the left, is not the same as the slope from the right.